Hello and welcome to the Side One YouTube channel, and in this video, SpotMicro Part 17, I'm going to talk about planes of reference. So in parts 11 and 12, we described how to calculate where the position of the feet are relative to the robot, or in other terms, in reference to the robot's body plane of reference. So this has worked well. We now know where our feet are by executing the forward kinematics, and knowing the position of each of the servos, which I have the shoulder, the arm and the wrist, we can calculate where the foot is in relation to the center of the robot. Now this is all well and good when the robot is sitting on dead level ground. We can get a fairly good idea of where our feet are. But if the ground's not exactly level, or if the robot does not have the feet in a level position, then the robot's mass, the center of mass of the robot, may not necessarily be within the boundary of the 4 feet, or even 3 feet if you have one of them off the ground, and that can result in the robot falling over. So we're going to actually have a talk about the various different planes of reference that we can look at, and then we're going to work out the maths to work out which one we should be dealing with. Okay, so in the GitHub, I'll have this document roughly around the same time the video comes out, uploaded into the GitHub document section. You'll find a link in the description to that GitHub repository, so you can have a read through all of this and the program code I've developed. I haven't completed the program code as yet, as I'm still working through the actual inertial measurement unit, which is located in the robot, and you can see where I'm at to that in part 3. So the planes of reference that we're using on the robot, as I said before, we have been using the body's plane of reference. So we know where all of our kinematics have calculated out where the feet are in 3D space relative to the robot frame of reference. And while this is good, it is not necessarily correct relative to the center of mass of the robot. But before we get too far ahead of what the center of mass is, let's have a look at some of the other planes of reference. So I've actually described the robot plane of reference, and as the name suggests, it's based on the robot itself. So based on the center of the robot, or in the middle of the robot, is the point of origin. And we're going to call that coordinate 0, 0, 0, or X, Y, and Z will all be 0, smack bang in the middle of the robot. And all the locations of the feet will be relative to that reference. The X axis will run across the robot from the left to the right, the Y from the front to back, and the Z straight up and down through the center of the robot. Now, this does not matter what orientation the body of the robot is in relation to the ground. We are describing in relation to the body of the robot only. And the kinematics described in parts 11 and 12 work off that plane of reference. Now, it's very important that we keep that in mind, because it is a very different plane of reference to the ground plane. The ground plane of reference is where the ground is, and in our case, it'll be located somewhere under the robot, and it runs parallel to the ground, as in the X and Y axis is across the surface of the ground, and Z runs up and down. And in our case, we will have that Z pass through the center of the robot, or somewhere through the robot. Moving on, we've got the feet plane of reference. So the feet plane of reference is pretty straightforward, and there's actually 4 of them. Because the feet may not all be at the same level, we use 3 of them in a tripod format, to create our feet plane of reference. And any 3 feet can form a plane of reference. There's a pretty good bet that if the robot's balance is over the center of the coordinates made up by the 3 feet, that triangle, then that will be the ground plane of reference as well. Not necessarily for any other combination, just where the center of mass is. And within this documentation, I've actually listed the 4 planes of reference. And I've actually specified one of the foot feet in the middle. So if you look at, say, the F foot plane of reference front left consists of the front left, the front right, and the back left feet. But we don't have to go into too much detail there. In theory, if all the feet are on the same level, then all 4 planes of reference will be the same anyway. It's just trying to figure out which of those 3 feet has the active plane of reference. Now, center of mass plane of reference, I've got a typo there. That one is located wherever the middle of the center of the mass of the robot is. So let's assume you've built Spot the way I have in the first 7 videos. It will be roughly middle of the robot. But if you then turn around and you mount a big massive LiDAR on the top front of the robot, you're going to move that center of mass forward and up. So adding anything to the robot will change its center of mass, and it's something that we need to be aware of. Now, I've added into the program code in under variables at this stage a location where you can actually program the center of mass offset in X, Y, and Z. So let's move on. That's where the origin is, by the way, for the mass of the robot. The inertial plane of reference is another one altogether, and we get that from the inertial measurement unit known as an MPU 6050, which was installed into the robot in Part 3. So, in theory, with a 6-axis acceleration slash gyro inertial measurement unit, we can tell how fast the robot is accelerating linearly, that is forward, back, left, right, up, down, or rotating, accelerating in a rotational manner. Again, around the z-axis, around the x-axis, or around the y-axis. So we can use that to calculate out what kind of accelerations are happening in the robot. Now, assuming that we've got the robot standing still, or sitting, as it was at the start of this video, then there will be a constant acceleration equal to gravity pushing down on the robot. And that will actually be, in the case of the robot sitting, it will be a component of the Y and the Z axis. And based on that, we can get a pitch. If the robot is leaning over to one side, then we will see a roll where it is slightly lower on one side than the other. And that again is between the X and the Z axis. So with those in mind, we can actually work out the pitch and roll of the robot. Now, in theory, if we rotate the robot, we can also capture the yaw, which is the rotation about the Z axis. At the time of recording, there is a bug that makes that data unreliable, but I don't need it for the examples we're going to use. Now, we can combine this inertial plane of reference, and technically its origin is in the center of the MPU 6050 chip on the breakout board. But we can actually combine the inertial plane of reference with the center of mass plane of reference. Use the in this case, the direction of the planes coming from the inertial plane of reference and combining it with the origin of the center of mass plane of reference. That gives us a hybrid plane, and we can use that to help work out where the center of the robot is relative to its feet. So if it's going to fall over and how we're going to do it. So I've described all of that here in this document. It does get a little bit heavy at times, but let's work through it. It's not that difficult, and we can use the information we've already got from the Forward Kinematics. So knowing the position of each of our servos, we can now apply Forward Kinematics. That gives us the coordinates of the feet relative to the robot frame of reference. And because we know where the center of mass is, we can apply an offset of the center of mass from our robot plane of reference. And that difference we can add to or subtract from our feet coordinates. We can then calculate out a triangle from the center of mass, or I should say a straight line from the center of mass of the robot out to the feet, each of the feet. And we can calculate out based on the angle, and we can use from the center of mass. We'll do that, the easy one first. We can calculate out the line and calculate out how long that line is. Once we know how long that line is, we can also calculate again the angle of that line. And we've done the trigonometry already when we were doing the kinematics. So a lot of this should be familiar to you already. To make life easy, let's do this 2D maths. So we're only going to look at, say, the XZ plane first and then the YZ plane. And we can use, so here we can see we've got the center of mass, foot left X is equal to foot left X coordinate minus the center of mass X. And we do that for the Y and the Z as well, so we can get those three variables. In a sense, or in effect, we need to do this for all feet. Once we have those coordinates, we can calculate out the length between the foot and the center of mass. And we're going to use, in this case, FLXZL, so that's front left X, XZ plane length. And you would have seen this formula before. It's actually a bit of Pythagoras. And to get the length, it is the other two sides of the triangle squared, added together, and then you get the square root of that. So we take com FLX squared plus com FLZ squared, get the square root of that, and we've now got the length for that first one. We repeat that for the y-axis as well, and we get the YZ length. That's the easy one. So once we've got that, we need to work out what the angle is between the robot's plane of reference. So the center of mass plane of reference until you apply the inertial is actually the same as the robot plane of reference. So we're going to calculate that out. Again, we're going to use Pythagoras theory, and we're going to calculate the front left XA. So front left X coordinate A angle, and that's equal to the reciprocal sine. So in the case of programming in Python, it's actually A sine. And that's com FLX divided by the length of that foot, so FLXCL. And that gives us an angle. Now, keep in mind, in Python, that angle will be in radians. But that's not a major drama, because it turns out that the pitch and roll values coming back from our IMU in my robot lab is also in radians. So that's an easy add together. And that gives, we'll calculate out this angle for both. Once we've got those two, we'll add the IMU roll and IMU pitch, and then we can actually calculate out now where the foot is based on its length, based on the new angle. And we can calculate out the X, the Y, and the Z position, which we'll call IMU FLX, IMU FLY, and IMU FLZ. So that's the X, the Y, and the Z coordinates based on the inertial and center of mass, origin and plane. We run this calculation or set of calculations for all 4 feet. And once we've got those, we're in a very good position to work out, is the robot going to fall over if we lift a foot? So this is where we need to work out where is the ground. So if we're planning on lifting, say, the front right foot, we need to make sure that the robot's not going to fall over because the center of mass is hanging over that foot or near that foot. So what we're going to do is actually draw a line, in this case it's an imaginary line, between the front left foot on the ground and the back right foot on the ground. Now I'm going to go out a little bit here and make an assumption that those 2 feet are on the ground. If they're not, this is not going to work. But let's work on the assumption that those feet are on the ground. We need to work out, if we look at just the XY plane on the ground, we've got the front left foot is in one position XY, and the back right foot is in a position XY. And if you were to draw that on a bit of graph paper with our origin for center of mass as the 0, 0 coordinate on that graph, we've got our foot coordinates already. We can actually work out a slope on that line, and that's not really that difficult. We take the front left Y, subtract off the back right Y, and then divide that by the front left X minus the back right X. And that gives us the slope. Once we have the slope, what we really need is the point where the line intersects the y-axis, which is in a standard slope coordinate system or coordinate equation, B. So if we look at a standard slope line formula, you get this y equals a times x plus b. And that's what we're trying to work out. So by calculating out our slope for the front left to back right, we get a, and once we've got a, we can transpose this equation, y equals ax plus b, to b is equal to y minus ax. Since we know a, and we can use, say, the back right foot y and x coordinates to transpose for x and y, we can now gain b, or calculate out b. And if we've calculated out b, we know where it intersects the y-axis. Now, if that value is positive, then that means that the center of mass is actually below that line, and the weight of the robot is being rested between front left, back right, and the back left feet. We're safe to lift the front right. If it is a positive, so if it's a negative number, that means that the back left foot can be lifted. If we need to calculate out, can we lift one of those other 2 feet, we draw the line using between the other 2 feet. So we'll draw the line between the front right and the back left. And again, if the value is positive, then we can lift the front left, and if it's negative, we can lift the back right. So hopefully that didn't get into too much maths. In the next video, I hope to actually have the program working, and we can actually start to do some translational moves to make sure we maintain our balance before lifting a foot. If you like these videos, don't forget to click on like, subscribe, ring that notification bell. It's a form of support. It costs you nothing and helps me a great deal in bringing these videos to you. If you'd like to help the channel further, I do have a Patreon account. Big thanks to my VIP Patreons, Go Lucky and Lorenz Berger, as well as my Builder Patreon, MRL 45. There is a link in the description to my Patreon account. Also, in the description is a link to my Discord, where you can join the growing community and ask for help if you need it while building this robot. And we'll see you in the next video.